lecture, because this afternoon we have a special lecture, which is on more recent topics.
Not only, I will also make a brief survey of some more old things, but mainly yes.
So, did you start recording? Okay,
Yes.
so I'll leave you because I have to meet the director, so when you're done with that, I'll be there.
Okay. Is it on?
Yeah.
Good. So now I'm going to tell you about alternative approach to the description of spin glasses below glass transition. This is also about infinite range model, Shenton-Kilpatrick model mainly. But it will be no any replicas. So this is a purely dynamic approach which reproduce most part of the same glass properties as we discussed in terms of replicas. So we need to start from what actually was discussed already once, dynamics above TC, and then we will see how to continue below, where non-ergodic features in these dynamics appear. So a few slides to remind about dynamics. We are interested in this correlation function of spin, local correlation of spin on the same site as I at different times. And we define a simplest dynamical process which is consistent with equilibrium state described by Gibbs distribution with the Hamiltonian written here. And again, it is simpler to start with a soft spin version of, instead of spins plus minus one, it is also can be done, spin plus minus one and discrete metropolis dynamics. But it is simpler to start to use the model of continuous spins. So each spin has double well potential described by sigma squared and sigma 4 terms, as written in these lower lines. So this is our dynamic equations, and psi of T is a thermal noise. The correlation function of this thermal noise is determined by fluctuation dissipation relation. So it is white noise independent for any for different spin I and j, and coefficient is just determined by classical FDT relation. So this coefficient is related with dissipative coefficient gamma naught and temperature, but here temperature is hidden. Beta is inverse temperature. Then we will calculate correlation function, pair spin correlation function C, and the linear response function J. These functions are related, again, fluctuation dissipation theorem. We are related in this way. And normally it should be temperature here, but in these notations it is absent because
May I ask you,
Yes.
why it is cubic in sigma?
Because I use here to simplify this derivation, I use a model for spin which is soft spin. Nothing more. So it is quadratic and cubic. Good. Then we proceed with dynamic generating functional, which is written in such a way that it is actually an integral of a delta function of equation. This delta function is exponentiated. Let me write it again here. We write it like integral of a sigma hat at each exponent I sigma hat t. Here is staying our, when it is integral over time and sum over all spins. And what is staying here is just equation equal to zero. What is equal to zero according to the dynamic equation? Now, in addition, of course, we should take care of Jacobian, because in this way, we average delta function of equation instead of its solution. And so there is some Jacobian V, which is, for this type of dynamics, it is very easy to calculate. It is given simply by the integral of second derivative of this same Hamiltonian over sigma. And then all correlation functions, response functions, comes as derivatives of this z over sources. L hat is coupled with sigma hat, and L is coupled to sigma. In order to get a correlation function of sigma, you differentiate. If it is pair correlation function, then you need to differentiate twice over L. Is it clear? Probably yes. Now, in but I should say that one term is, no, it's okay. So you see here, there is a term which is quadratic in sigma hat. Sigma hat here and also sigma hat here. This term, Hi is simply external field. External field which enter the Hamiltonian in a way that H E sigma E integral of time. But remember, in this equation of motion, it was some noise, Langevin white noise. And this expression is obtained after averaging of this Gaussian noise, so it comes linear with sigma hat, and this is why we got this term here, sigma hat, sigma hat. Now we need to average over random couplings J, ij. And here we simply can average directly without any replicas, because with functional z in the absence of external sources is equal to 1. It is constructed in a way to be equal to 1. This integration of a delta function with appropriate Jacobian.
Okay, but for the high order connected with functions, we first must to derive with respect to differentiate with respect to the sources, and then put it equal to 1.
And put sources to 0.
To 0.
Yes, but it doesn't change anything because sources are not mixed with j, ij. It is an averaging of couplings. J is independent on the sources.
So it is true also for the high moments.
Of course, because all these moments are calculated by you differentiate a necessary number of time, and then you put sources to 0. So integration over this random j gives you this 4 order terms with 2 sigma and 2 sigma hat. Next point is you decouple this 4 order terms to reduce them to quadratic terms. And in order to do it, you introduce matrices in time space Q 1, 2, 3, 4. All these Q are matrices because when we average over J's, we come to non-local functional. It was double integral over time because, of course, J are time independent. So you have this integral over time squared. Decoupling. These are quadratic forms in this Q1, 2, 3, 4. And then here, L is a Lagrangian which contains these matrices in linear way and 2 sigma, or a sigma hat, sigma, or even this sigma hat, sigma hat. So this is Gaussian integration. Actually, only one of these Q matrices is 0 because otherwise it would be a violation of causality principle. And there are 2 others are equal. So what we actually have is 2. Here I just denote these matrices. One of them becomes J, correlation function, and another is C. J is response function and C is correlation function. I should remind you that originally, before we make this averaging over couplings J, we had a term quadratic in sigma hat, which was just a constant. It was this term. After we average, we got additional contribution with J. J squared and correlation function. And similarly, we get this additional term into the inverse in the bare response function. Here, this j minus 1 was just a constant and this dissipative term with I omega. And this is addition due to interaction with other guys. Also, we need to remember that this equation of motion, which we are solving, is nonlinear because we have these terms here. Or in Fourier space, it looks like this. This is my probably last part of reminder. Above TC, we are looking for renormalized kinetic coefficient, gamma, which is simply a derivative of inverse response function over omega. And for this quantity, we have equation like this. Denominator comes exactly due to coupling between spins. Then here we have some quantity, this, which comes due to nonlinearity of interaction. This sigma is can be expressed in terms of diagrams in this way. J, J, and C. Of course, with double integral. And here, with vertices, U and U. We don't know, we will not calculate this sigma because what the only thing we need is that this derivative is finite when omega goes to 0. And this we can easily show after we find the solution. So the main point which comes from this equation is very simple. If we find a temperature coming here such that denominator vanishes at some temperature, then this will be a critical point in terms of dynamics as well, because it means that this quantity diverges. And this quantity is nothing but relaxation time. Is it clear till now? Is it clear? Good.
And we are assuming implicitly that the spins are not a dynamics, they are frozen, and they are not affected by the back.
They are not frozen. In which sense frozen?
The back acts only as a thermalizing.
Well, the only thing we assume is that derivative of this self-energy is finite. Nothing else. Because if it is finite, then it simply adds some finite constant to this bare relaxation time. Yes?
The fact that the divergence here is beta minus beta critical, so it is the exponent is 1. This is somehow related with mean field?
Yes. Yes, yes. This is purely mean field theory. And we don't know how to extend it to, for glass, to something more realistic.
But what the experiment show in such type of glasses, so
completely different exponent. Completely different. But my goal today is to demonstrate how to use this kind of dynamic approach to describe irreversibility, or in other terms, non-ergodic properties.
to do as much as possible within the new field.
Yes. So now we go below TC. It is here. It is written. It is the same thing, but new point is the following: that we will now consider temperature to be a function of time. Temperature below TC. This is again the same equation. Now here you see this beta j at time t and at time t prime. And the crucial point is the following. We know already from replica approach that below TC there is some special kind of order parameter. Q is a correlation function which do not vanish with time, and delta is anomalous contribution to response function, which is we have seen this anomalous contribution when we discuss the difference between zero field cooling magnetization and field cooling magnetization. Now let us split full correlation function and full green function in these two terms. This with tildes will be short time response. And it is a function of t minus t prime. While anomalous paths, q and delta, in principle, they are not function of difference. They are function of two time arguments, t and t prime. Now we repeat the same derivation. Adding very slow noise with z is a slow part of noise. The correlation function of this noise is just our q. And total magnetic field which acts on the system can be written in this form. It is this noise and also anomalous part of response function. Here we see sigma and this delta. Our goal is to derive self-consistent equations for these order parameters, q of two arguments and delta of two arguments.
That was what I was thinking about. These correlators here of this noise are have a spectrum which is much more sharp than the delta function of the initial thermal noise. So
why sharp? In which sense?
Not they are the thermal noise is fast.
Yes. Yeah. And this is slow.
And that is slow.
This is very slow noise.
Otherwise, the things become messy.
Yes, yes. Well, the important assumption here, which is valid for mean field model, but not invalid for usual normal spin glasses, is that we can sharply differentiate between fast dynamics at short time scale and very, very, very slow dynamics at which describe non-ergodic properties. That there is some window where nothing happens. Fast dynamics already relaxes to equilibrium, but this equilibrium is incomplete in the sense that it is equilibrium in presence of a given configuration of slow field. And this is a way to get rid of fast dynamics completely and to derive self-consistent equations for slow noise. This is maybe more or less what I was saying now. Now this at zero frequency limit of response, fast response function, J tilde, is given by this equality. It is one at zero time, minus magnetization squared. Magnetization at time t. And this magnetization at time t is an average over fast dynamics of a spin at time t. Now we can come back to Ising spins and to write a equation for magnetization in this form. This is a recall, it is a effective random field which depends on slow correlations, and it will depend on history as well. And this is just external. So one important point is that below TC, this denominator is always zero. It is the same marginal stability conditions which we already discussed previously. Therefore, the correlation and response function go as a power law frequency. In particular, J of omega tilde should be here also. It is some fractional power of omega, which can be shown to obey such an equation. Nu is this power, and this cotangents, and this is beta function, and all that is expressed via average over slow noise of this combination of magnetization. That expression was derived in the paper of Sampolinsky and Zepelius. Then, using different ways, for example, by Taulis-Anderson Palmer approach, we can find that in the limit of zero temperature, this exponent goes approaching 1/4, while at transition temperature it is 1/2. This 1/2 we already found before. And now, equations for slow response. here all time differences like t minus t prime and so on are supposed to be very long. So all this short time dynamics came to equilibrium. This anomalous response, delta T1, T2, is a derivative of magnetization at time T1 over field which was applied previously at time T2. Then susceptibility is this 1 minus m squared, and it is just the same as usual expression with 1 minus mi squared is 1 over cosinus squared h I beta. Good. Self-consistent equations looks like this. Correlation function naturally is the average of m of time t, m of time t prime, and averaged over this slow noise. And for anomalous response, the equation is this. We are, you see that this equation is linear on the left-hand side, and on the right-hand side, it is bilinear in terms of this delta. So in order for this equation to have a non-trivial solution, we absolutely need to fulfill this condition. Again, it is a marginal stability. If it would be not fulfilled, then the only solution of this equation would be just zero for anomalous response. This is a complicated equation, but it becomes much simpler close to transition point. First, close to transition point, when this tau here is 1 minus t over tc. We know that in the main approximation, the order parameter q is qtt, coinciding time. So it is main approximation, it is linear in tau, but using marginal stability condition and the fact that average of m to the 4 is 3q squared, because of Gauss just weak averaging, there are 3 ways to pair this magnetization. So there is a coefficient 3 here, and this way we find that q should be tau plus tau squared. Then equations for delta and q functions simplify a lot, and you see these two expressions. Still, these are integral equations in terms of time. And here, tau is a function of time, t2, t1. Here again, we see. So the meaning of these equations is follows. Suppose we know how temperature was decreasing below Tc, just some function of time. Now, for this given trajectory of temperature in time, we want to find these order parameters, slow correlation and slow response. Of course, there is some Is it still running? This integral equation has a rather big symmetry, namely reparametrization of time as like some function of time is defined as another time variable t, time with tilde. As long as this function is monotonous, nothing changes in these equations. The only change is that anomalous response with delta shouldn't be multiplied by the derivative d tau 2 or d tau 2 tilde. So it means as long as we move in one direction, only decreasing temperature, it doesn't matter how fast or how slow we do it. But the condition that this evolution is monotonic is absolutely crucial. Because if it is not monotonic, then, well, first we look for a solution for monotonic. For monotonic cooling, after we understand that reparametrization is trivial, we can choose the simplest linear variation of temperature with time, like this. Linear, and if you put yes,
for finite range glasses it is no longer so. I believe, I think that this reparametrization also is a consequence of infinite interaction in Feigel'man path, because you immediately can go anywhere fast.
Right.
Anywhere fast.
Right. For finite range system, there is additional phenomenon. I mean, what I'm describing now is a history dependence in spin glasses. Another phenomenon, which is called aging, is present for real spin glasses, and it is absent in mean field model. Aging, it is just what the statement that reparametrization does not affect the result is just this. In other terms, it is a statement that there is no aging. Does not matter how slow you move along the trajectory. For real spin glasses, it is not the case. And how to describe this phenomenon in terms of some real microscopic theory is a big question.
So, I mean, I see here the analogy with SYK model, which is also of distances model, and reparametrization works until some point. You can then add some little part, and then you have Schwarzer.
In SYK, the story is much better. I mean, here you can derive effective action for this reparametrization mode, and then to find many interesting things. How to do it for spin glasses? A good question. Nobody knows. It is worth to try. So if we use this simplest trajectory in time, we can check that solution for Q and delta is also rather simple. This correlation function is determined by T prime. This is if T is larger than T prime, then Q is just given by T prime. Otherwise, in the opposite limit, it is given by T. Of course, it should be symmetric. And now, for anomalous response, as long as T is larger than T prime, this anomalous response is T prime. This is the exact solution of the equations which were written here. When I also put H to 0, no external field. And you can just check that these equations are solved by these linear functions. What it leads in terms of observables. Field-cooled susceptibility is given by this expression. Naturally, according to definition, you set some infinitesimal external field and above Tc, and you are interested what will be magnetization at time t. This magnetization is integral over T prime of this response function. This is full response function. It contains fast part and slow part. Fast integration of a fast part over time gives you 1 over q t. It's the same FDT relation. And integration over slow part is here. For zero field cooling, you would get only this part, fast part. So this integral is just the difference. And how this difference scale with tau? T, delta is linear in T prime, and then you have also integration here over T prime. So altogether, it gives you second power in tau. And this is this is just the difference. So it was like this for zero field cool susceptibility and constant for field cooled. The difference near TC, the difference was quadratic, and this is what we get here. Now, let us compare results of this slow cooling dynamics and replica symmetry breaking. In lowest order in T minus Tc, they coincide. But we do not coincide exactly. For slow cooling, the second next order corrections can also be found, and we are given by these additional terms. And using this solution and marginal stability condition, we can find QTT, which is nothing but Edwards-Anderson order parameter, up to rather high order in tau. And this result is a little bit different from replica result of Zommers, but only in the fifth order in tau. All previous orders coincide. Similar situation is with internal energy. In dynamic approach, we can express internal energy, which is just this sum, in terms of our order parameters, Q and delta. The expression is like this, and it leads to expansion up to fifth order in tau in this form. And again, we find that it is different from replica result in tau in order 5. Then, of course, well, first of all, we do not understand seriously why we are different. But just we found that we are different. On the other hand, it is not very surprising, because this slow cooling is not supposed to give really equilibrium result. It is just a result of evolution of the system when we change temperature with time. It is not necessarily equilibrium. On the other hand, it seems that it might be more physical quantity, because anyway it is impossible to reach equilibrium in spin glass. You would need to wait infinite amount of time. While the result of any cooling procedure for any kind of trajectory is something which you can see in experiment, simply speaking. Now I am approaching the most interesting part of this story. We discussed already many times this hierarchical structure of spin glass state, which comes out of Parisi theory with replica symmetry breaking. And schematically, it looks like what is shown here. You decrease temperature, your order parameter grows, and the number of different metastable states also grows. Metastable states are such states which do not talk to each other. Just you come either here or here or here and stuck there. Now, let us consider a non-monotonic evolution of temperature with time, like this. Tau increases, so temperature was going down. And then at some point we go back, warm a little bit, and then continue. We can expect that during this detour up in temperature and then again back, we will smear out some part of history in the system. We may expect that it forgets something. If we come until this point, for example, we come to such a branch. Okay, but when we warm, and here, if we warm here, then all these three branches come together. So we don't know where we have been before this warming. This is just picture. Now let us look what our equations tells us. The same equations in lowest order in tau. But with non-monotonic cooling, the solution is this. It is again given by two T prime, but only in this path when T prime is less than T1, or in this path, T prime is larger than T2. But there is no memory in this region between T1 and T2. This memory was smeared out because of this temporal annealing. It comes simply from solution of these equations. Surprisingly, this solution is in full agreement with qualitative consideration which I was presenting. There is some indirect relation to experiments in real spin glasses. Even indirect because what we consider here was actually aging, which we cannot even describe in this scheme. But nevertheless, this was a measurement of imaginary part of magnetic susceptibility in insulating short-range spin glass with cadmium, chromium, indium, S. So what we did is they cool to temperature below transition, 12 Kelvin. Critical was 16.7. And we measure out of phase magnetic susceptibility. As function of H, H is just the time between cooling of the system to this temperature and starting the measure. The longer we wait, the smaller is this high double prime, which is dissipation. So dissipation considerably decreases because the more they wait, the more close to equilibrium this system appears. Now, they cool again to lower temperature. The same process of slow relaxation of high double prime goes during this interval. And then they warm back to 12 Kelvin. You see, nothing like this, no original peak. Just this curve continues, is extending the original path. If, say, we simply forget about this interval, which was shown here, just take out this interval, move, we see continuous curve. This is an illustration how important is even not very large change of temperature. It strongly reshuffles all this short time dynamics. Good. So the main thing which I was going to explain you in this lecture is just that there is a relatively straightforward way to derive such a property of anomalous response if your trajectory is not monotonic. You cool, you warm, you cool again. Of course, you can solve these equations for any kind of motion, including, say, here it was magnetic field, H was put to 0, but of course we can make it some trajectory in HT plane. Here it will be TH. It will be some irreversibility line, the Almeida-Taulis line. And then we can go here and do any kind of trajectories in the plane of temperature and magnetic field and find what will be magnetization. For some complicated trajectories, these equations you will need to solve them numerically, but it should be not big deal. The major point is that indeed we have analytic means to describe this history dependence, literally as a dependence on the shape of trajectory. Below, as long as we come to this region, below irreversibility line, anomalous response appears, and it can be described by such equations. Now, a similar approach to a little bit different system, which we have done at about the same time. It is also glass, but now it is not spin glass, but superconducting glass. Actually, it is in superconducting glass you even can produce physically the object which will be described by mean field theory. Namely, this is an array of superconducting wires, vertical, horizontal. On each intersection, there is some Josephson junction, the tunnel barrier, which gives you some weak Josephson current. Each wire, in terms of its order parameter, is characterized by the phase of order parameter in the middle of the wire, or at the end, but doesn't matter. But just single phase variable describe the state of this wire. Then, in terms of the full energy is just sum of these Josephson energies on each intersection. But here phi is a phase which comes due to magnetic field. We put all this array into magnetic field, which produces phases like Aij is the integral of vector potential over x between points I and j. Very straightforward. If this magnetic field is large compared to this magnitude, here n is the number of wires and small l is the average distance between neighboring wires. As it is drawn, actual distances are random, just random Poisson number with given average. It means that phases introduced by magnetic field, which stays here, they are random. Or they can be absolutely random if magnetic field is sufficiently strong, or some partially random. But anyhow, we deal with a frustrated system because of this magnetic field. So below some temperature, it freezes into a phase glass. Instead of Ising order parameter, here we have order parameter like exponent e to phi xy of the parameter. And one of the simplest observables for such a system is diamagnetic response of this array, which appears if we change magnetic field below glass transition. Magnetization, this is a kind of non-classical superconductor in the sense that there is no Meissner effect. If you cool this system in a constant magnetic field, it will not produce any diamagnetic response just because it is a glass. But if you first cool and then try to change magnetic field, then it will be diamagnetic response, and it is determined by such a relation. First term here is simply the result of this dH over dt is, in other terms, thing which is proportional to electromotive force. Time varying magnetic field produce electric field and so normal currents. By the way, I forgot to say that here dynamic equation for phases is constructed in the following way. Current between wires I and J, which have some intersection, is usual ohmic current here, because phi dot is a voltage. Time derivative of phase is a voltage. So this is a voltage difference between two wires. This is normal resistance. And this is a Josephson current. Then the only thing you need is to write down Kirchhoff equations, which tells you that sum of the incoming current is equal to sum of outgoing current. And that's it. Then this is how you get dynamic equations for these phases phi. Zeta is a thermal noise, exactly like in spin system. Yes. So above TC, these correlation functions have some finite time of relaxation. Here is a difference. So this term is proportional to omega, like this term. This is also omega. So above TC, the response is purely dissipative. But below TC, we have the same, we split correlation and response functions into fast and slow paths, exactly like with spins. And here we also can derive equations for these slow paths. This is one equation, and this is another one. It is not exactly the same as for Ising model, but similar. One reported difference, for example, you can see here. I assume that both temperature and magnetic field may change. So I want to describe a trajectory in the plane of temperature and magnetic field. And if it was changed, then H1 minus H2 enters this equation here and there. Most important is how diamagnetic response is expressed via our anomalous functions. And this is shown here. Again, it is a bilinear form. So this is slow part of correlation function, and this is slow part of response function. And now let's consider some simple trajectory, which is shown here. We cool, it is not shown here, but I assume we cool across transition temperature. And then just make some small delta H. If it is very small, we can neglect it here. And then solutions of these two equations will be just the same as for spin glass model. Here, Q is proportional to tau, delta is proportional to tau, and then there is one integral. So altogether gives us the result that the magnetic response is non-zero, and it is a third power of T minus Tc. The paper which I mentioned here is an experimental paper on superconducting ceramics. It was in early times of high temperature superconductivity, these objects usually were not single crystals, but some kind of granular system. And in particular, in this work, we used this granular system, and to study its response to magnetic field. So we found something like this type of irreversibility. Now, let me make a detour. The approach to this slow dynamics, which I described for Ising model, is not the only example of such an approach. In particular, there is a useful paper of Crisanti, Horner, and Zomers, who consider p-spin model where many spin interact all together, like this. But we simplified this model using spherical constraint instead of usual constraint when the length of each spin is equal to 1. So spherical means that the only constraint for sigma is this. Single constraint for all n spins. Of course, it simplifies a lot the problem, because you can treat this constraint by introducing just a single Lagrange parameter. It should be also a function of time, because this constraint should be fulfilled at any time. But it is only one additional variable.
Mikhail, who suggested or somebody else with spherical model?
Look, Volodya, you see reference. 1993. Zomers, Horner, Crisanti.
It is this people, right?
Yes. The model was, I think they proposed this model. Kulyandel, Kurchan developed it a lot in many respects. But I'm not completely sure, but I suspect that these guys were the first.
At least one of them I know is Zomers.
Well, he has many important papers on spin glasses in this period of time.
But he also was very active in chaos.
Mm-hmm. So for this model, we can derive equations of a, roughly speaking, of the same kind as what I told you before. It is this. You see, R is some, I think it is something related to the constraint, to the spherical constraint, and then mu is up to some number, it is temperature as function of time. B, it is external field as function of time. Eta is Langevin noise, but here it is already renormalized. You see, here it is correlation function in power p minus 1. In our problem, which I told you before, p was 2, so here it was just correlation function. But for p-spin model, it goes c in power p minus 1. And in the equation, it goes with response function and correlation function in power p minus 2. So generally speaking, the form of these equations is similar, but properties of them are different. For example, here I show it is a phase diagram in axis of magnetic field and temperature for specifically p equal 3, which they found in this paper. Here at strong magnetic field, on the right of this black dot, there is a single second order transition. But at smaller magnetic field here, there are two transitions. The full line this full line is a first order transition found from these dynamical equations. First order in the sense that Q jump from 0 to some non-zero value. It is not continuous. And I remind you that when we week ago discussed replica symmetry breaking approach to this p-spin problem, then we also found that the transition is of the first order in the same sense. It is not a thermodynamically first order transition because any observable is integral of either over replica parameter x, or like in this approach, it is an integral over time. So there are no nothing like jump in entropy or in specific heat. They are continuous. But the order parameter defined like this may experience a jump. And this is what happens here. Moreover, this broken line is the temperature of discontinuous transition in the same model obtained by means of replica theory. Replica theory for this p-spin model also gives you discontinuous transition, but at a little bit lower temperature. So here the difference between dynamical approach and replicas is even more prominent. In Ising-Spin glass, the difference, as I told you, was only in higher order, in T minus Tc. And here it is seen immediately. Good. So I come to conclusions. First of all, this slow cooling is indeed an alternative with respect to replica approach, and I would say that in terms of what is, I would expect that results of slow cooling are more close to physical reality, because it is just some well-defined process which you follow. And also, you may consider very different trajectories in the plane of or space of parameters. The trajectory which I was discussing with simple variation of field after field cooling is just the most trivial one. But you can study any trajectory. And then these equations give you direct access to non-ergodic behavior when you have non-monotonic variation of temperature and field. There are not so many studies of which this slow cooling method was used, but it is not because it would be very difficult, but rather because nobody tried. And here I suggest few not difficult problems to play with this approach. So for this lecture, that's it. And if you have questions, please ask them.
What are the main physical causes of the difference between the replica and this approach?
I suspect that the difference is that in slow cooling you follow this branching of this hierarchy, and you always choose some branch. Somehow in some random way. So in other terms, in a replica symmetry breaking approach, the quantity which you consider to be equilibrium, say, energy, is energy of each metastable state, which is weighted in correspondence with the total energy of the state. So they are not equal because energies of these different metastable states, they are different. they contribute in a with different weight to this absolute equilibrium quantity. While in slow cooling, I suspect, they are all equal, because you just choose at each branching, you choose your way randomly. So, well, okay, of course it is qualitative interpretation. I'm not sure it is correct, but it seems reasonable. Okay, if no questions more, then just we have a lunch break.